Hi guys, this is Mr. Mellor. This is our lecture video on net force and equilibrium from chapter 4, section 2 of our textbook, in case you want to read the textbook to get additional clarification. All right, so we're starting our project on designing bridges, and the goal of any bridge design or any structure design, any building, is to ensure that our buildings don't collapse. And in physics speak, we say that is making sure that our objects have no acceleration. And so to ensure that that is the case, we have Newton's second law to help us out. Acceleration is caused by the net force and limited by mass. And previously we had said, well, how do you find net force? We use free body diagrams, which are diagrams, FBDs, free body diagrams, of our forces in any sort of system. And so in this little scenario right here, we have a man is applying a force, F applied to the right. We have the force of friction acting opposite to that. We call that F friction. Then we have the normal force, Fn, keeping our object from sinking to the ground. And then we have the force of gravity acting downwards. Okay? And we can sum that up in horizontal and vertical components to find out how the object's motion is going to change vertically and horizontally. And when we talk about bridges, we make sure that the sum of the forces horizontally and vertically is 0, such that we have no acceleration. That's the entire objective. Okay, so when we have bridges, we have trusses typically. And trusses are great because they redistribute forces from the very ends of our bridge to the center. But in order to be able to understand them, we have to recognize that those trusses cause forces to act at angles. Right? And so here's a simple example to make sure we know how to deal with forces at angles. We break it up into horizontal and vertical components using trigonometry. Okay, what is trigonometry? One more time. Well, trigonometry is, we know for any angle, we have predefined ratios. And we call those predefined ratios for any angle sine, cosine, or tangent. All right, and so imagine I was trying to pull on this block upwards at an angle of 30 degrees from the horizontal. And we would recognize if I was pulling upwards, then this overall pull upwards in an angle, we would have a y component. And I'm also pulling to the right, we have a horizontal x component. Okay, and so if I wanted to find those, I could say, well, this is the opposite leg from this angle on a triangle. This is the adjacent leg from this angle on this triangle, and this is the hypotenuse. And if I were to write that for my forces right here, I'd have FPY, FPX, and I have FP, F pole. And so in our vertical motion, we have FPY ends up being equal to FP times sine of the angle. Horizontally, we have FPX is equal to FP cosine of the angle. How did you get there, Mr. Mellor? Well, we start off with our ratios, right? Ratios of the lengths of any sides are predefined. We know that the angle is 30 degrees. Our adjacent leg for cosine is FPX. Our hypotenuse is FP, so I multiply by FP on both sides to get it to cancel on the right. And I'm left with FPX is equal to FP cosine of theta. And if we were to use our calculator, we would find out that's 0.88 or 0.86 times 50. And we get, that's about 43 newtons to the right. Okay, vertically, we are trying to find this component of our overall force. Right? And so we would write, well, that's the opposite leg. We're going to use sine for that one. Sine of our angle, 30 degrees, is equal to FPY over hypotenuse, FP, multiplied by FP on both sides to get it to cancel on the right-hand side. And we're left with FPY is equal to FP times sine of our angle, which is 30 degrees. And we get 50 times 1/2, which is 25 newtons. Okay, so What if it was a little bit more complicated than that? If I had a scenario where, say, there were more than one force involved, right here we have the force of gravity, Fg equals m times g. We have the normal force, Fn, pushing up. We have the force of friction to the right. And what if I was told, Mr. Mellor, I need you to make sure that the sum of all these forces adds up to 0 so your bridge doesn't collapse. What should my, pulls be such that we want to make sure that vertically everything cancels out? What should my horizontal component of my pull be such that we're not moving horizontally? So we have the force of pull in the x direction, and we have the force of pull in the y direction. Okay, in this particular scenario, let's say that we're choosing to accelerate to the right, and we are not moving up and down. Okay, so our overall acceleration vertically is going to be 0. Our overall acceleration horizontally is not going to be 0. If I wanted to find the net force, and I wanted to list out the steps, I'd say define the problem, identify the variables. Okay, we do that by writing out our free body diagrams, recognizing any two-dimensional pull has an x and y component. Then we select a coordinate system and apply it to our free body diagram. Okay, well, coordinate system just means, what directions are positive, plus, minus. Or we could say move our plus and minuses. We could rotate our coordinate system to be at an angle like this, but that's more advanced physics. We're not going to do that. We're going to stick with the x and y that we see in math class. Okay, so next step, find the x and y components of all vectors. We did that previously. We said Fpx is 43 newtons. Fpy is 25 newtons. Not too bad. Find the net force in both the x and y directions. Okay, well, the net force in the x direction is equal to Fpx pointing to the right and the force of friction pointing to the left. So we have Fpx minus force of friction, and that overall is going to be equal to our mass times our acceleration in the x direction. All right, all we do is add these two values up overall. Okay, vertically, we have a different scenario. The net force vertically is equal to the normal force. Then we have plus the pull in the y direction minus the force of gravity. And we said that's equal to 0. And if we knew the mass, we would be able to find the force of gravity, the weight of the object. We know Fpy, and so we could tell what the normal force was in this scenario. Okay, and so again, what are we shooting for with this whole thing? With bridges, we want to make sure that bridges have the sum of the forces adding up to 0. And when the sum of the forces add up to 0, we call it this term equilibrium. All right? Equilibrium is a state in which no physical changes occur. What does that mean for bridges, for structures? It just means no acceleration. If our object's at rest, not moving, it's going to stay that way. And that's how we like our structures. We don't want them to move. Our equilibrium rule says that when the sum of the forces on an object is 0, the object is in mechanical equilibrium. Right? Great. Here's a couple of examples. We have a little girl, Nellie. She's being held up by 2 ropes. Force of tension, and we have the force of gravity downwards. And those all add up to 0. Same thing here. We have our friend Burl on the right-hand side, and our friend Hewitt on the left, and Hewitt on the right. And so we have a series of tensions upwards, and we have weight of the scaffold, weight of Hewitt, weight of Burl downwards. And those all add up to 0, and we're in equilibrium. Our scaffold's not going to start accelerating downwards. Let's do a little bit of practice problems. So if our goal of bridge design, any structure design, is make sure the sum of the forces add up to 0, and that's why we have free body diagrams, to be able to ensure that that's the case, to analyze our complex two-dimensional forces, break them up into horizontal, vertical, make sure they all add up to 0. Here's a little bit of a more simple scenario. Say we have Burl, he weighs 1,000 newtons, and he's on a scaffold that has the force of tension up in 2 different ropes. All right, Burl's 1,000 newtons downwards. The question is, what should if there's 500 newtons of force upwards right here, what should the force be right here to ensure that Burl doesn't accelerate downwards? 500 newtons. Right? Equilibrium is when the net force adds up to 0. Same thing here, 1,000 newtons downwards, 1,000 newtons downwards. Okay, we have 170 upwards right there. That means this must be 830. We have 0 newtons right there. 1,000 downwards. That means this must be 1,000 newtons. Okay, let's do a little bit more challenging ones. We have Nellie Newton. She weighs 300 newtons. All right, 300 newtons downwards. What must the force of tension here be such that she doesn't accelerate downwards? Such that she's in equilibrium. 300 newtons. Arrows pointing in opposite directions. Subtract. All right, here's a little bit trickier one. We have 300 newtons downwards. There are 2 different sensors upwards, but it's the same overall rope. So this is the only force-carrying object above her. These are actually going to both be 300 newtons. There's no reason to have more than one sensor right there, right? Because they're both holding up the exact same thing, 300 newtons. Therefore, they should both show the same value, right? There's only one rope to hold that force, and they're both attached to it. Over here, it's a little bit different. We have 300 newtons downwards, but there are 2 ropes, right? There's one rope that can hold some weight here. There's one rope that can hold some weight here. And if there are 2 ropes evenly spaced, they both can hold weight. Each one's going to hold 150 newtons. Same thing here, 300 newtons. Right? What should each of these be? Right, she's evenly spaced, so 100 newtons. Here we have the ground is pushing her up. We have the force of gravity. Then we have tension, 300 newtons downwards. These 2 are both supporting her, so 150 newtons each. Right? Here we have some complicated looking structure, but at the end of the day, it's only one rope holding her. So that must be 300 newtons to make sure the sum of the forces adds up to 0. So just to recap, what does this have to do with bridges? Well, the entire objective with bridges is to make sure we maintain equilibrium. If you look at these practice problems with Nellie Newton and our friend Burl, and you were to rotate scaffolding, right, you would see that, in fact, that's just a bridge that's upside down. It's the exact same problem. All right, practice more in class. We'll see you then. Bye, guys.